This master's program is a 12-month affair and starts in September and goes on to early September the following year, based on interfacial engineering of advanced interfacial materials. And interfacial materials has really developed in the past decade or so to become its own separate discipline, really, based upon chemistry, physics, material science, metallurgy, crystallography, thermodynamics, etc. So the interfacial engineering of these advanced materials really focuses on how to boost their performance in a whole wide variety of applications, for example, in chemical sensors, medical devices, the pharmaceutical arena, or else in powder technology with nano materials and nano powders, selective membranes, nanoscale membranes, for example, for gas separation and gas capture, selectively so. Also in renewable energies, such as solar energy, photovoltaics, and of course, catalysis, for a very wide range of different photochemical and energy transformations. And really, if we look at mankind and man's interest in interfacial materials, this spans all the way back from the Stone Age to the beginnings of the Iron Age, where we first began to manipulate metals, and then all throughout the Middle Ages, and then up to the 20th century, where we first began to develop steels, stainless steels, alloys. And then, of course, in the 1950s, 60s, when we began to look at polymers and ceramic materials, composite materials, and of course, even amorphous materials. And the emerging discipline of interfacial materials and interfacial engineering really is based upon the whole idea of exploiting what we know about the microstructure and the phase diagrams and the thermodynamics and kinetics and catalytic properties and surface properties, of course, as well, and morphologies, all of these important things. So this discipline is emerging in and of itself of interfacial materials and interfacial engineering, and is found, of course, in many, many different journals. For example, just a suite of journals is here, such as Advanced Materials and Composite Interfaces and so forth. As an example of some recent work that we have been doing in chemical engineering at UCD, we've been looking at, let's say, zinc oxide nanoparticles with a view towards hydrogen production, okay? So these zinc oxide particles could be present in the form of wires or spheres or cuboids, and by manipulating the molecular structure and atomistic structure of the underlying crystal lattice, we can do advanced predictive molecular simulations on the band gap properties, and then in turn both predict and measure the, for example, photocurrents when we have different biasing potentials to look at and examine hydrogen production rates. Okay, and we can look at surface defects and oxygen vacancies and so forth. So within chemical engineering at UCD, we've got state-of-the-art laboratory facilities, for example, for multi-phase flow. We've got membrane reactors, membrane bioreactors. We have a pressure swing adsorption system for gas separations, atomic layer deposition, various photoelectrochemical facilities, solar simulators, potentiostats to work with solar cells, AM1 light source, and of course, lots of laboratory facilities to prepare these materials, some of which may be proprietary. That there's an active invention and innovation scene in our department, and patents lodged and so forth. And of course, we have access to plasma deposition systems as well. In terms of the course content, it's a 90-credit 12-month master's. There's a 30-credit summer research project, and then design work and taught courses throughout the year. You can find more material on the associated brochure with this course, but I've provided a brief overview here of some of the core and various optional courses that you have across a wide area of different interfacial engineering areas. In terms of the uniqueness of this program, well, there's very few programs at postgraduate level worldwide that are really focused on interfacial materials or surfaces and so forth. So this is the only master's level degree that's specifically in this area in terms of advanced materials. And the market size in this interfacial materials area is expected to grow very substantially over the next decade to almost double in size from $4 to potentially $7 billion or even $1 trillion per annum. I mean, world GDP is about $85 trillion. So you can see that interfacial materials makes up a very healthy percentage of that. There's many career opportunities in interfacial materials in Ireland. For example, the medical devices sector is very prominent. And of course, Augenis Illumina, analog devices, and many, many different aspects of the pharmaceutical industry. And of course, semiconductor industries, which are very, very advanced in Ireland, with many of the key players there.